All right, good morning. Sorry to be gone again. As you can probably tell from my voice, not feeling great. Both of my boys are homesick. It's kind of infirmary around here, so sorry to do it to you, but want to stay on schedule and not fall too far behind. So we got a couple videos, 10-1, day 2 or day 3 here, and then we'll start on 10.2. Both of these are pretty quick. So you can see here in terms of what the title of the section is, length of a parametric curve. So we've obviously graphed those parametric curves. That's what you've quizzed on. So what we're going to start with is this idea that if we have our XY plane and then we graphed our parametric curve. So let's say it kind of looks like this. The way we could figure out sort of what this is, let's say I wanted to figure out like the length of this line segment right here, this guy, or this curve. It's not really a line segment. But what we could do is set up a right triangle where our right angle is going to be right here. And then this would be similar to our hypotenuse. Okay. Obviously, the hypotenuse is implied to be straight. With this curve, it's going to be an approximation. But like many things we've done, we start with the idea of an approximation. We ultimately kind of find a limit of it and then deal with the idea of the infinitely small interval. So that's what we're going to do here. So this would be, we'll call this our change in X. This is going to be our change in Y. And then we'll call this L for the length of that curve. That then sets up what we have down here. All right, that if we set up the Pythagorean theorem that the length squared equal to the change in X squared plus that change in Y squared, take the square root of both sides, we initially get a plus or a minus, but since we're looking for a length, can't be the negative. So it sets that up for us to approximate the length of this, okay? Now, obviously, it's going to be an approximation. We would want to do more, so we would want to do another one here. And if we did a right triangle in here, do your delta y, your delta x, and then ultimately we would want to start adding all those together. We'd want to start doing more and more of them, so that's where that little Riemann sum comes in. What you'll notice, though, is in parametric, we don't just simply have an x and y position based on each other. That's kind of what this is implying. In parametric mode, our x position, our change in x, is based upon that corresponding change in time. Same here, that our vertical change isn't just the change in y, it's our change in y according to our change in time. So this really becomes kind of a delta x is always related to our delta t. Same here, this is our change in time. All right, so that's why this, which is just delta x delta y squared, just becomes the dx dt, so delta x over delta t over delta y over delta t. As this limit, or as we find more and more of these, as n goes to infinity, that's why these deltas become a little dx, as well as when we do the limit of a Riemann sum, that is what the definite integral is calculating for us, okay? So it's really pretty simple. In terms of where it all comes from, not really a big deal. But really, you just want to walk away from this set of notes, just knowing that this is the length when we are looking for a parametric curve, okay? From there, it's pretty straightforward. I don't know if we'll do all these because it's pretty simple. And I know you're on the video, probably don't want to listen to this voice too long. But the length of our curve, let me come down here and leave a little space, is the integral, in this case from 0 to 2 pi. And then it is the square root of our dx dt squared. So we're going to 1 our dx dt. Hang on a minute here. All right. So that's our dx dt. The dy dt is just going to be 3 cosine of t. Throw it into our formula. Like so, and then one of two things will happen. Most of the time, I'm probably going to ask you to just throw that into the calculator and give me the decimal. This one can be cleaned up a little. It actually is somewhat clever here. If we were to simplify this would be 9 sine squared. This would also be 9 and then cosine squared. If we then went ahead, factored out that 9, hopefully you're writing smaller than me, I would get 9 times sine squared t plus cosine squared of t. So then we would all know that this is really square root of 9 is going to be 3. This is a 1 overall. So actually, let's just multiply these together first. This is 9 times 1, which is 9. Square root of 9 is going to give us a 3. I should have our dt's at the back of this as well. So let me add those in. And then now we can actually do that pretty quickly. Do your 3t's, the antiderivative from 0 to 2 pi. The upper limit gets plugged in first, minus the lower limit, which is a 0. That then is the length of that curve. All right. All right. If you also kind of look at this, some of the stuff I've done in the past, isn't this a circle? So if I were to ask you to graph this, that should be a circle because these both have 3's in front of them. That circle should have a radius of 3. Well, if we're talking about the length of a following curve, isn't that what circumference is giving us when we talk about a circle? 2 pi times your radius. Our radius, looking at this, having quizzed on it, understanding these coefficients, and we move them over, we write all that fun stuff, is a 3. Then when I go ahead and plug that in, we get our circumference to be 6 pi. And that's pretty much the definition of circumference, correct? It's the length around a circle. Same thing we got using the calculus of it. They're not always going to be circles, which is why we can't just rely on the circumference formula. This formula here will work for any parametric curve, okay? So that's that. If we go to number 2, same process. I need dx dt. That's going to be pretty simple, 2t. dy dt is going to be 3t squared. The length of our curve, in this case from 0 to root 5, is the square root of dx dt squared plus dy dt squared. Much like when we did the length of the curve back in the day, a number of people actually missed this. I kind of mentioned how it's really common for people to forget those squares. Same here, so just be careful. You could just plug that into the calculator. I may ask you to simplify it. This would be 4t squared plus 9t to the 4th. That could be your answer. We'll kind of stop there. I would have you go through that by hand. All right, number 3, I'll leave you that one. If you wanted to go through, it actually plays out very, very similar to number 1. That's a circle from 0 to pi, which means it's really just a semicircle. So if you understand this is the circumference of a semicircle, we're only going to want half of that. You could really go through all of that with the parametric curve formula. And what we should get is pi, because this has a radius of 1. The circumference of a circle is 2 pi times your radius. This here would tell us we only have half of that circle, so that's why I divided by 2, so those canceled. So it's really just pi times a 1. Circumference is going to be a pi. So you can kind of do that one if you like. Again, I'm not feeling particularly well, so we're going to cheat and scoot along. It really is just getting this formula memorized. Okay, I've never really seen that expanded and tested in any other way. I wouldn't test you in any other way. You'd either be setting it up, or once it's set up, you're going to do a math 9 on it. All right, the next one. 10.2, day 1. It's called vectors in a plane. That's sort of what we get into here in 10.2 for a few days, is the idea of these vectors. And you actually do this a little bit now in the integrated math stuff. So some of this hopefully is going to be a review. And certainly if you're in physics, you've seen a lot of it. So a scalar is a finite quantity whose magnitude is represented by some number. So measurements such as force, we haven't dealt with a lot of that. We certainly talked about velocity. We've certainly talked about displacement. They require a scalar. All right, and that's just kind of the magnitude, how big, fast, the scale of it. And then a direction. So direction was really important with our velocity. The positive sign, negative signs would tell us if we move left or right. Same with a displacement. If we have a negative value for our displacement, it means our position decreased. Positive value means it increased. All right, so this tells us how much we increased, the scalar, and this would tell us sort of in what direction that we've increased or decreased. All right, a vector is represented in a plane by a directed line segment. The length of that line segment is its magnitude, so that is important. All right, we'll be finding plenty of those. So the length of the line segment is its magnitude. And the arrow would then obviously indicate its direction of motion. So when you see this here, so let me make this a little bit bigger, and it's hard in the vector thing. It looks like a ray, but what you want to understand when we're referring to this as a vector, that this is our direction. So you'd have A to B. It's a directed line segment with an initial point A and a terminal point B. So we don't continue on forever from A to B. All right, in an array, you would start at A, and then this arrow tells us we continue on forever through the point B. If it's a vector, it means we start at A, and then we finish at B. All right, and that's what this is referencing here. If we throw some absolute value bars around it, that's referencing the idea of the magnitude of that vector. The magnitude of the vector, again, is the length of that vector. Okay? Because, again, this doesn't mean that we're going on forever. Last bullet point, vectors are considered to be equal or the same if their magnitudes are the same and if they are moving in the same direction. With that, that's what I kind of want you to do here in this first one, is just show with that idea in mind that the following vectors are equal to each other. So in order to be equal, same magnitude, moving in the same direction. All right, so if I'm going to take A to B, first thing I'm going to do is show our direction. So if I just wanted to figure out sort of what direction are we traveling, it's really nothing more than kind of that slope. Up 2, right 1, up 5, left 2, so on and so forth. That's giving us our direction, the path that we are taking. So if I do it with these, I'm going to do 4 minus 0 over 3 minus 0. So this is going to be for the vector drawn from A to B. So that's our path. We're going up 4, right 3 throughout that vector. If I go ahead and do CD, so now I'm going to use these points. I'm going to do 6 minus 2 over -1 minus a -5 or -4. So we'll get a 4 on top. These double negative give us a 3 on the bottom. So the idea that we are traveling in the same direction, we've satisfied that. Oh boy, I don't know what just happened there, but I don't know what just happened there. Let me move this down a little bit. All right. The next thing then is they need to have the same magnitude. So the length of them. All right. So this is, you can think of it a few different ways. We're going to think of it right now as that distance formula, right? That's how we can figure out the distance between 2 points. That would be the length of that line segment is the distance between them. If you remember, the distance was your change in x squared plus your change in y squared, similar to what we just did in that first part of the notes. So I'm going to be doing 3 minus 0 squared. Just, this is for A, 3 minus 0 squared, and then 4 minus 0 squared. Going to get a 25 in there. The magnitude of that vector, the length of that vector of those 2 points is square root of 25, which is 5. All right, so that directed line segment drawn from A to B has a length of 5. If we do the same thing with the other one, so now we'll do these 2 guys. Again, just our distance formula. I'm going to do -1 minus a -4 squared. 6 minus 2 squared. Again, this is going to give us a 3 squared, which is a 9. It's going to give us a 4 squared, which is a 16. Another 25 underneath that. Our distance is 5. So these directed line segments from A to B and then from C to D, they're going in the same direction. They're going up 4, right 3, up 4, right 3. They have the same length to them. Those would be considered equal vectors. All right. All right. Component form, which is what we'll deal with quite a bit. Component form of a vector is where our vector is equal to our first vector plus our second vector, or what we're going to deal with quite a bit, is the vector is AI plus, and then notice how that I is bold, and then you have the B, and then the J is in bold. Component form is implied that our initial point is 0, 0. So that's where our vector is going to start. And then we're going to go out to whatever A and B tell us. A and B represent the scalar. So that's how big of a movement we make in either the X direction or the Y direction. And that's what these are telling us. I is the positive X direction. J is your Y direction. Excuse me. Some vector operations real quick. If we ever wanted to add vectors, so vector 1 plus a vector 2, all we do is add up their horizontal changes together and make that the coefficient of our I. Add up your Y, your vertical changes together, make that the coefficient of your J. We're going to show how that plays out here in a second. Subtraction, same as addition. We would just subtract their like parts if we saw that. If we have scalar multiplication, it really is as simple as just distributing. And then the same with number 4. If you have a negative coefficient, we're just distributing that negative. Really pretty simple stuff here. So for these first couple, all you're going to do is find the following sums and difference, write your answer in the form AI plus BJ. And this really is as simple as the thing as we've done all year. So 2i plus 3i would give us 5i. And then we add up our j terms. The negative 7j plus the 6j would be a negative 1j. That's our answer. Now, I do like kind of showing what this just did and what this is actually showing us. So I would suggest sketching this in real quick. So drawing an XY plane. And I'm going to do this vector first. This is component form. So that is implied we start right here at 0, 0. And my horizontal change from there is 2 to the right. And then since this is a negative 7, I'm going to decrease my Y position by 7. So 5, 6, 7. So I started here. Here is where I finished. So it's kind of like if I'm standing here and I rode this vector, this directed line segment, this is vector number 1. All right, so now I'm standing right here. But what we're going to do from there then, now that this is my new location, this is where this took me, now I'm going to see where would this now take me from that new location. So from that location, I'm now going to move right 3. So 1, 2, 3, and then up 6. So 1, 2, 3, 4, 5, 6, and then we'd be right over here. So now I'm here after that first initial vector took me here. I'm going to write out this vector, and I'm going to end up right there. So we went this direction, and then we caught a new vector, took us to this direction. All right. Now, what does it mean in regards to this? Look at the vector that we just ended up with here. If I know, this is saying if we would have just added those vectors right from the beginning, we could have headed off and saved ourselves a lot of distance and time. Because now look at 5. 1, 2, 3, 4, 5. And then a negative 1i. Wouldn't that have taken us straight to that same location if we would have just added them right from the beginning instead of treated them as 2 different vectors? All right. So that's what that is doing when we add our vectors together. It just gives us a shortcut to get to where those 2 vectors would have taken us. All right. So with that, we don't necessarily need to show this one. Hopefully you understand that. We don't need to overcomplicate this because this is super easy. You're just going to combine like terms. So clean it up a little bit. You're going to distribute that negative 2. Add your like terms, and then that's our new vector. All right, finding vector is given 2 points. So if I have point 1, point 2, then the vector drawn starting at point 1 and going to 2 is just the difference between their x coordinates plus the difference between their y coordinates, and that's our horizontal change, so that's the I, and then the vertical change, which is going to be your j. So it says find the vector form from the following 2 points. So if I wanted the vector form from point 1 to point 2, I'm just going to do this. So 5 minus a 3, that's my new I position, plus subtract your y's, 1 minus a 4, that is my new j position. All right, so if I did 2i, I was going to change this to a negative 3j. Negative 3j, and then that would be our answer. All right, so now, I again, probably last time I'll have you do this. I want you to, I want you to sketch it either way. Maybe I lied about the last time. I want you to sketch something in here. Okay, so let's sketch this out. Go to the point, 1, 2, 3, 1, 2, 3, 4. And that's this guy. And then let's go out to the point 5, 1. That's this guy. So we went, this was our first point. This is our second point. So this is the vector drawn from one point to the other. So this is P1. This is P2. Look at what we just wrote here. So let me try to do this somewhat accurately. This is now component form, saying that we're going to start at the origin. My horizontal changes 2, so right 2, and then I'm going to go down 3. So 1, 2, 3. So then that point is down here. We're going to connect those. And then hopefully yours is a little better than mine. This isn't too bad. But notice, even though they're not in the same place, taking us to the same spot, what we talked about before, as long as they have the same direction. So if we looked at those definitely appear to be parallel. You could count the slope if you wanted to confirm it. And the same length / magnitude. And again, you could do that work if you wanted. But just kind of from the eye test, looking at it, those are the same vector. They're equal vectors, even though they're in different locations. Okay. All right, 2.1 to 0.2. So I'm going to do 4 minus 1. That's my I. Plus a -2 minus 9 as my j. So the vector that we would get from 0.1 to 0.2 is a 3i minus an 11j. All right, 3. Very, very much like our parametric. Really, if you think of vectors, if you haven't kind of started drawing that parallel yet, which is why we do it right after parametric, these vectors are really parametric equations. This gives us our x position. This gives us our y position. We're calling them I and j. We're using a fancy word like vector, but it's largely the same idea in terms of how we can define these. So if I wanted to figure out what vector do I form from 0 to pi over 6, this unit vector. So I would just say the vector drawn at pi over 6, you're just plugging in. So the cosine of pi over 6 is √3/2. That's our I position. And the y position at pi over 6 is 1/2. So that is your j position. All right. And the same thing. Take this 2 pi over 3, plug that in. So even I got to kind of refresh a little bit here. All right, so 2 pi over 3 is over here. We want the x position over there. That should be a -1/2 I. And then the y coordinate up here should be the positive, and then the y coordinate at our pi over 3 angles is √3/2. All right. All right, last but not least, length of a vector. This is the one that I was kind of lying about before. I do want you to draw this. So draw the vector formed by this. The vector in component form, 2i plus 5j. So that would mean I start here. I would go over 2, up 5. 1, 2, 3, 4, and then 5. Started here. So this is our direction of our directed line segment. That is our vector going out to that point. Second sentence, reading here, notice the vector represents the hypotenuse of a right triangle. So you could definitely create a right triangle out of pretty much any vector, most of them. Therefore, the length of that hypotenuse, so this guy right here, isn't that really just the hypotenuse of a right triangle? So if we start talking about the length squared equals, we'll call this A just for the sake of what I have written here, and then our vertical change will be B. Then the length of our vector is the square root of A squared plus B squared. And then typically you will see this written with those absolute value bars here. So I'm just going to erase the L, replace it with the idea of the vector and the magnitude of that vector. It's just the length of this vector. Whatever that gives you, that's the length of our vector. So it's magnitude. All right, so for number 1, we're really just using this guy right here. So the magnitude of my vector, if you wanted to draw out a right triangle, you're more than welcome to, is the square root of 3 squared plus a -1 squared. So the magnitude of this vector is what? 9 and 1, √10. Magnitude of this vector, again, just using this little formula right there, is the square root of the -2 squared plus 3 squared. I'll give us a 4 and a 9. So this has a magnitude of root 3. That is the length of that vector if we were to sketch that thing out. Okay? All right, hopefully that wasn't too bad. Both of these typically go pretty quickly. People understand them. A lot of this you would be familiar with as well. Hopefully I will see you tomorrow. All right, thanks for listening to my voice and paying attention. We'll see you soon, hopefully.